Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to find the number of terms in a given alternating series to have an approximation with the precision that we want. So we generally approximate infinite series because infinite series means like you have infinitely many terms to be added. So that's very hard to guess what the sum could be if you don't have a formula for finding the sum. So we generally approximate infinite series by keeping some number of terms in the series. So in this particular case, we're going to find, in fact, how many terms we should keep so that the error should be less than 1,000th. Okay, and we have a special theorem to be used in this direction. It's called the alternating series remainder theorem. So if you have a convergent alternating series, so that means you apply the alternating series test and you know that the series is convergent, and if ANs are non-increasing, which means AN plus 1 is less than or equal to AN, then the absolute value of the remainder, what does that mean? So you have the sum, which is represented by capital S, and you have the partial sum. Partial sum means like I'm keeping only finitely many terms in this sum. So S, the actual sum, minus the partial sum, is the tail of the infinite series. So this theorem says that the absolute value of the tail, which is Rn, should be less than or equal to AN plus 1. Let's say like you cut off at AN. So you're looking at the sum A1 through AN, you cut off, and then that's your partial sum, that's your approximation. So then the tail, the absolute value of the tail, cannot be greater than the very next term where you cut off. Okay? So again, this is a very special theorem to be used in approximating alternating series. We have two of those series, so I picked two very relevant series to work on. So why don't we hit the road, because we have a long way to go. All right.
All right, first of all, let me just correct this typo here that there's no S here. So there's only one condition to check, which is a decreasing condition. We have a convergent alternating series. Let's say like I have minus 1 to the n, how about that? Minus 1 to the n, or n plus 1. It's okay. A n, okay? And we have this condition to hold true, which essentially means that an is the non-alternating part is a decreasing sequence. And this theorem says like the absolute value of the remainder satisfies the following. Okay, so who is S here? Who is S sub n? Who is Rn? So let's check that out. Since it's a convergent series, then the sum has to converge to the sum S, right? So S is the value of this infinite sum. And if you expand this out, so it's going to be A1 minus A2 plus A3, the sign alternates. Let's say like we keep going all the way to the n term, okay? And the very immediate term is minus 1 to do n plus 2, an plus 1, and on and on and on, okay? So here, the very first n term and the sum of that is called S sub n, okay? And whatever you call the tail here, which has infinitely many terms, is Rn, okay? So in other words, the sum, the infinite sum, is the sum of the partial sum plus the Rn, the tail, okay? So this theorem says, or this theorem provides us the relationship between S, Sn, and Rn in terms of An plus 1. It says that S minus A, Sn in the absolute value, which is the absolute value of the tail, right? Because S is the sum of Sn and Rn, right? So the absolute value of the tail cannot be greater than the very immediate term in the tail, right? The non-alternating immediate term in the tail. Okay, that's a pretty strong result because Rn has infinitely many terms, and you add them up, that sum cannot be bigger than this one term An plus 1. Okay, so we're going to sort of like apply this idea to approximate this sum by partial sums, but we don't want the tail to be greater than 0.001. So you want it to be smaller than that. So we want the approximation precise up to 0.001. Okay, let's just sort of tackle with this problem. And let's go here. So I'm going to grab an out of this. The non-alternating part is a n here. And I want an plus 1 less than or equal to an. Is that correct? Well, 1 over n plus 1 quantity squared is always less than or equal to 1 over n squared, because here you're dividing by a bigger denominator. So this equality should hold true, right? So then going back to the remainder theorem, it says like the actual sum minus the partial sum has to be less than or equal to n plus 1. By the way, since in the description of the remainder theorem it says like we have a convergent sequence to start with, it's your task right now, maybe by pausing this video, to prove that this is a convergent alternating series by checking the two conditions of the alternating series test. Okay, one is that the limit of an is 0, which is in fact obvious because this tends to 0, an equals 1 over n squared. And I already showed that n is decreasing, so it's a convergent series, we know that, and it converges to the sum s, and s minus the partial sum, me keeping only the first n terms in the sum, taking the absolute value is the absolute value of Rn, and Rn has to be less than or equal to, by the remainder theorem, an plus 1, which is 1 over n plus 1 squared. Okay, so the tail, okay, after you take the partial sum, is the amount of error, because you discard that part, right? And the amount of error, you want it to be like less than 0.001. Okay, I want this to be less than or equal to, let's say less than, right? Strictly less than 0.001. Okay. So now the question is like, what should n be? So how many terms I should keep in this sum? Because n depends on the partial sum. Partial sum tells us exactly how many terms we're going to keep in the sum. So capital N has to be determined here. So I'm going to rewrite that inequality here. And we're going to sort of like guess what n could be. So this is in fact 1 over 1,000. Okay. So you can pause the video and try different values of n. Start with n equals 1. So you keep only one term, so this becomes 1 over 1 plus 1 squared. That's 1/4. 1/4 is not less than 1,000. Okay. If you keep two terms, this is 1 over 2 plus 1 squared. That's 1 over 9. Still not good. Go to maybe n equals 30, for example. 1 over 31 squared, that's going to be still less than 1,000. I think that the best here is n equals 31. So let me just write here, n equals 31, so that this number becomes 1 over, let me just clean this, 1 over 32 squared, and that's equal to 1 over 1,024. Obviously, 1 over 1,024 is strictly less than 1 over 1,000. So that means that based on this analysis and alternating series remainder theorem, I should keep 31 terms in the sum to approximate the actual value of the infinite series to have an error less than 0.001. Okay, I hope this is clear. I hope the analysis is clear. Students get confused about this argument all the time. I hope I explained this well. But we have another shot to go because we have part B.